All right, hello everybody, and welcome to the new normal. So today we're going to be talking about total orbital angular momentum. So this is another way of saying that we are going to be talking about how we can combine two various the angular momentums of two various electrons to combine to generate a new total orbital angular momentum. So this one might be especially important, as you can imagine, because angular momenta are a good stand-in for magnetic fields. So if I want to go ahead and figure out how my electrons behave around an atom, I probably want to figure out what the total magnetic field is around this system, which will be dictated by my total orbital angular momentum, which I'm going to represent as a uppercase L, which should be noted is not the orbital angular momentum vector, which we've used that symbol before, nor is it the individual orbital angular momentum, which is a lowercase l. I'm going to try my best to keep these guys separate. So very similar as to what we've been working with for combining spins and spin-orbit coupling. It turns out that my orbital angular momentums can couple together from the orbital angular momenta of the various individual electrons and can combine either constructively if they're both pointed in the same direction, whether that direction is along the z-axis or in any other space, or they can um, combine deconstructively where they're pointed in opposite directions, and I'll have a net zero total orbital angular momentum. Now, as you can imagine, as this system gets more complicated, there's going to be a lot of possible values. And we can help distinguish what values are going to be possible and which ones are not using something called a Clebsch-Gordon series. So that's the idea where I can combine my two orbital angular momentums and say that they can either combine constructively, L1 plus L2, adding in the same direction, or they can be slightly offset and there'll be that sum -1 and then -2 if they're increasingly offset till eventually the point they're pointed in opposite directions, and my total orbital angular momenta will simply be the difference of my two L values. Now it's important to note that we do put a absolute value on this difference to emphasize that we have a minimum value of 0, because it turns out that our total orbital angular momentum quantum number is indeed going to be a quantum number, which means it's going to be representing a magnitude, not a direction, so we can't have a negative value. And in order to aid with this, we typically use our larger value of L, if they are different, as our L sub 1, and our smaller value of as L sub 2. Now, this can seem a bit much, so let's try and extend this idea to a real system. So let's go ahead and apply this to a system containing 2 electrons in the d orbital. So if I have this case, then L sub 1 is going to equal 2, and so will the orbital angular momentum of the second electron. So this means that I can have several possible combinations, the first of which they will be my 2 electrons will be pointed in the same direction, which will have my 2 orbital angular momentum adding together to a total value of 4, and then -1, 3, -2, 2, all the way till I get to the difference, 2 minus 2 of 0. So this gives us 5, not 4, possible values of our total orbital angular momentum: 4, 3, 2, 1, and 0. And to make this matters a little bit more complicated, these spectroscopists love giving all of our various total angular momenta value their own symbol, which will actually turn out to be handy later. And we give these symbols uh, a value of gamma, and these should look fairly familiar, as these are more or less the same letters we used for the individual orbital angular momentum, except for now that I'm dealing with a total case, I use the uppercase version. So if I have a total orbital angular momentum of 0, I have a symbol of S. If I have a total angular momentum quantum number of 1, I have a symbol of P, D, F, G. And if I had a value of 5, it would be H, I, J, K. We rarely end up having symbols greater than I, but it is useful to know that they're out there. So this, these total orbital angular momenta can actually be fairly useful as they help set our the magnitude of our magnetic field around my entire atom. But it turns out that that isn't everything, as it turns out that if I'm dealing with magnetic fields, what often matters to a certain degree more is what direction that field is pointed in. So I need to try and be able to extend these total orbital angular momentum into what directions that angular momentum can be pointed in. And by convention, as usual, we're going to try and quantify to what extent this orbital angular momentum is going to be pointed in the z direction. And we do this using the total magnetic quantum number. And again, just like the lowercase m sub l, or magnetic quantum number, this is just going to tell me what degree of my orbital angular momentum is pointed in the z direction. And it can be defined very similar as the m sub l for my individual orbits, as it can have values ranging from 0, plus or minus 1, plus or minus 2, all the way to plus or minus my total orbital angular momentum, as my orbital angular momentum can either be pointed all up, all down, or any integer value in between. So again, this can be fairly useful, and we can apply this to our 2d electrons, who have a maximum total orbital angular momentum of 4, which means that they can have possible total magnetic quantum numbers ranging from -4 all the way up by integers to a total value of 4. So this is actually fairly useful and can help us figure out the exact angular momentum values using our typical conversions by h bar of our orbital angular momentum pointed in the z direction. So this can be fairly useful, but let's be honest, can be a little bit arbitrary. So one of the ways I like looking at this is in a more electron structure configuration. So a good way of doing this is by taking our values, our total magnetic quantum numbers, and determining it using a Clebsch-Gordon series for the possible combinations of our individual magnetic quantum numbers. So if I have a maximum m sub l value of 2, because I'm dealing with a d electron, then I can either have both of my orbits pointing up for a maximum value of 4, or both of them pointed down for a minimum value of -4. So again, this can be quite useful and will give us the same exact values we got looking at deriving our total magnetic quantum numbers from our total orbital angular momentums. But again, I like looking at these more on an electron structure perspective, so I often like building these up using an empty orbital diagram and then filling in my electrons. So we can then, using this convention, say that my total magnetic quantum number is just going to be the sum of the two individual magnetic numbers, because I will have already taken into account the vector component. So my maximum value will be simply putting 2 electrons in the +2 orbital. And this will give me a maximum total magnetic quantum number of 4. Or I could have a minimum value of putting 2 electrons in the -2 orbital with a minimum magnetic quantum number of -4. And you can have any number of combinations in the middle, and I encourage you to kind of play around with these. For example, you can end up with a total magnetic quantum number of 0 through several cool tricks. First of which, I can have one electron in the -2 orbital and one in the +2, and they will cancel out to give me a total magnetic quantum number of 0. Conversely, I can also put both of the electrons in the 0 orbital, and it turns out if I do that, I also end up with a total magnetic quantum number of 0. Now, one of the things that I do want to emphasize is just because my total magnetic quantum number is 0 does not mean that the value for my total orbital angular momentum is going to be 0. A good way of thinking about this is I can have both of my electrons in this 0 state, which means that both of their orbital angular momentum are pointed in the z direction, or in the xy plane. And if they're both pointed in the xy plane, this means that there is a chance for them to be additive, which means there's going to be some combination that will give me a total orbital angular momentum of 4, not 0. So we'll get into that topic a little bit more later, but for now, I want to focus on a very specific piece of information that we can gain about our total orbital angular momentums from our total magnetic quantum numbers. And that's this idea that I know that my total orbital angular momentum has to have at least one total magnetic quantum number of the same value. So if I'm able to figure out the maximum value of my magnetic quantum number from an orbital filling diagram, I can also figure out my maximum value of my total orbital angular momentum. Now, this isn't really that important if I have 2 electrons, but as soon as I have 3 or 4 electrons, this can become quite important, because it turns out that not every single value of our total orbital angular momentum that we would hope can be occupied actually can exist. And let's look at this for the specific case of 3 electrons in a d orbital. So I want to figure out what's the maximum value of my total magnetic quantum number I can get. So we can do this by taking my orbital diagram and filling as many electrons in this positive region as possible. So the easy call is I put 2 electrons in the +2 orbital, and then I can't fit in a 3rd electron. So it means that I have to put that 3rd electron in the +1 orbital. So that means that my maximum value for my total magnetic quantum number is going to be 5, not the 6 I might hope for. And because my total magnetic quantum number can't be greater than 5, it turns out neither can my total orbital angular momentum quantum number. So that means that my value of capital L is going to be limited to 5 as well. So this is actually quite a useful trick as I get increasing number of electrons, and I restrict the number of places any additional electrons can go. It turns out that this is also going to be the reason why if I fill up an entire subshell, my total quantum number is going to be 0, because my total magnetic quantum number also has to be 0, because if I fill up every single orbital, all of my m sub l's cancel out. Now, this can be quite an important topic, but we're going to be dealing with this in a little bit more detail later, and right now we're just focusing on these big pictures. So I've been talking for a bit, so let's try and apply these concepts in a little bit more of a visceral fashion. So let's try and use our Clebsch-Gordon series to try and determine the possible values for our total orbital angular momentums and our total quantum numbers for any system with at least 2 electrons. And again, note that if you have a complete subshell, that our total orbital angular momentum has to be 0, because all of our angular momentum in that full subshell has canceled out. So let's go ahead and try and examine the possible total orbital angular momentums and their corresponding symbols for each of the following configurations. And if you're following the video along, feel free to pause after I introduce a new problem so that you can try and solve it on your own. So let's start with a relatively simple case. I have one electron in an s orbital and one electron in a p orbital. Well, in this case, my L1 is going to be 1, and my orbital angular momentum for my second electron is going to be 0. So my total orbital angular momentum is going to be a maximum value of 1 plus 0, which is 1, and a minimum value of 1 minus 0, which is 1. So it turns out for this case, I only have one potential value for my total orbital angular momentum, and that's 1. And it has a corresponding symbol of P. But it will have potential total magnetic numbers of 1, 0, or minus 1. All right, so we luck out a little bit when dealing with s orbitals because they don't offer anything to our total orbital angular momentum. So let's complicate this picture a little bit by going to 4 electrons. So I've got 2 electrons in an s orbital and 2 electrons in a p orbital. So for those of you who love your periodic table, you may note that this is going to be the valence contribution for carbon. So this one's kind of important. So in this case, we can ignore the S subshell, first because it's an S subshell, and second because it's full. So when I have a complete subshell, we can essentially ignore it. And I'm just going to focus in on these 2 p electrons. So L sub 1 is going to be 1, and L sub 2 is also going to be 1. So I can have a maximum total orbital angular momentum of 1 plus 1 and a minimum value of 1 minus 1. So this gives me potential total orbital angular momentums of 2, 1, and 0 with corresponding symbols of D, P, and S. So let's go ahead and walk our way up our orbital angular momentums and have 1 electron in a p orbital and 1 electron in a d orbital. And in this case, my first electron will have a orbital angular momentum of 2, and my second electron a value of 1. So this means that my maximum value for my total orbital angular momentum will be 3 plus 1, and my minimum value 3 minus 1. Or sorry, 2 plus 1, and 2 minus 1. I was looking ahead because our total orbital angular momentums are 3, 2, and 1 with corresponding symbols of F, D, and P. So again, this means that I will have potential values for my total angular momentum or total magnetic number ranging anywhere from -3 to 3. So for our last problem, let's go ahead and look at something that breaks the mold a little bit with 3 p electrons. So this one gets a little bit complex, and I encourage you to write out an orbital filling diagram, because you'll find that my first 2 electrons are going to occupy the exact same state I had when I had 2 p electrons. But that third electron will only have a m sub L value of 0 available, which means that my maximum value for my total orbital angular momentum will still be 2, with values of 1 and 0 still possible. And this means that we will have symbols again of D, P, and S with with total quantum numbers ranging anywhere from 2 to -2. So that brings us to the end of our introduction to total orbital angular momentum. We're going to be dealing with this topic in a little bit more detail later. But next time, we're going to be revisiting the idea of spin in a little bit more detail. Take care and have a good day.